All right, welcome AP students to your AP Unit 2 post lecture on polarity within a covalent molecule and a brief overview on the very short topic of metallic bonding. So ideally, we should have ended where we went through ionic compounds and solids, and I introduced, and as well as naming, and then I introduced covalent molecules and their solids. Nope, I'm about to introduce the solids, covalent molecules, and how to name them. Okay, that's ideally where we stopped. Was a complete. We're thoroughly done with ionic compounds. We have addressed the concepts of molecules, covalently bonded molecules, and now we're going to finish it up today. So, when we look at a molecule where there are bonds where electrons are shared, not transferred, we see that we can not only categorize an individual bond as polar or nonpolar, but we can actually take that and expand it across the whole molecule. So let's just start by addressing an individual bond's polarity or an individual bond's relative electronegativity differences. So remember, electronegativity is the ability for an electron to attract, ability of an atom to attract another atom's electrons toward itself within a bond. So we say that polarity, is really a discussion / quantification of the electronegativity differences, I'm going to abbreviate as E/N, between two atoms in a bond or between two bonded atoms. Okay, two bonded atoms. Another way of putting it is we're really trying to see how the electrons are shared. Okay, that's another way of looking at this. It's really just talking about, well, how are they exactly shared? Because if we're sharing electrons, it doesn't mean it's always equal, right? Kind of like when you share with your siblings, doesn't mean it's always equal. So we categorize bonds in three ways, right? Which shouldn't be too much of a surprise. So first, the third that I listed is the obvious one, which is ionic, where it's no sharing. Superpolar is another way of putting it. No sharing, superpolar, and you actually are so anti-sharing that you do a full electron transfer. We're already familiar with this degree of polarity. But what about like the more in between stages? So we can have sharing occur, but unequally. So polar bonds, polar covalent bonds, are when you're still sharing, but it is an unequal sharing of electrons. And we actually put a value to that. When we look at the electronegativity differences between the atoms, we say that the electronegativity difference, remember a triangle means a difference, is somewhere within the range of 0.4 and less than 1.7, okay? And actually, I don't think it's equal to, I think it's just straight up less than 1.7. And then nonpolar is when we have truly equal sharing of electrons. And that would mean our electronegativity value ranges anywhere from 0, okay, to less than 0.4. Now, if you're like, wait, where are these numbers coming from? Okay, so we actually quantify electronegativity through a scale known as Pauling scale of electronegativity is what we call it, Pauling scale of electronegativity. And here, maybe I'll just move this over so we can clearly see it, okay? And what it does is it offers us a relative value to assess how electronegative an atom will be when it's in a bond, how likely it is to be greedy and pull the electrons closer to it, even though it's technically sharing, or of course in the ionic version, it's so greedy that it just snatches it away, right? So what you'll see is that the electronegativity values go from 0 to 4.0, and they're very non-precise, right? You don't see any 0.11116, right? It's just these are the values. And you'll notice that they follow the trend, that the higher the electronegativity across a row and up a column, the greater, okay, the greater your Pauling scale value is. Okay. You'll also notice that for the most part, noble gases don't really have an electronegativity value, except for xenon, which kind of starts behaving slightly differently. And of course, that the highest electronegativity value is fluorine. Fluorine is the highest electronegativity value because, as we know, fluorine is the highest Coulombic attraction experiencing atom. And it's also a halogen, which means it's desperate for getting one more electron. Okay. So we say there's a little kind of quote that we say that all roads lead to fluorine when we look at periodic trends and particularly electronegativity and ionization energy. Okay. So we can also non-numerically, but illustratively show when there is a partial charge or a separation of charge or an unequal sharing. So when I look at a bond, let's say I have the bond between, we have to pick a polar value. So we know the electronegativity difference between the two atoms that I give has to be between 0.4 and 1.7. So let's say I have boron, okay, bonded to nitrogen. Let's do nitrogen. Okay. I don't know. We'll just do an example here. Boron has a electronegativity value of 2.0. Nitrogen has an electronegativity value of 3.0. So the difference between the electronegativities is, well, the absolute value of the difference between the two, okay, is 1. 0.0, making it a polar covalent bond. It is still technically sharing, okay, but it's not sharing well. And what we would say is if we didn't want to write all the numbers, we could also illustrate this unequal sharing with an arrow known as the dipole moment, okay? And what we say is that there's a more positive partial charge and a more negative, okay, more negative partial charge for the nitrogen. So what does that really mean? Well, if I, okay, were to illustrate how the sharing is happening right now between boron and nitrogen, okay, it's like my electrons are being shifted more over toward the nitrogen. All right. Now, please don't ever draw an actual like bond like this. I'm just trying to give you an illustration. All right. It's like my negative electrons are held more closely by my nitrogen. So it's almost like I'm creating a region of negativity. And I have a region of slight positivity. So what we say then is I don't have a full charge because a full charge would mean I'm ionic. I have a full transfer of electrons. I'm still sharing, but it's like, all right, I have a slightly more positive zone and a slightly more negative zone. And this delta is the Greek symbol that we use to represent partial positive. Okay, partial, okay, is in lowercase delta. I could also simply draw a dipole arrow, which represents the same thing. My dipole arrow has a positive cross end toward the more partial positive side in a bond, and it goes toward the negative end. The arrow ends up on the more negative side of the bond, okay? So a dipole occurs when there is a difference in electronegativity, right? That's the whole principle, is that we have covalent compounds or covalent molecules, covalent bonds that are still sharing, but they're not sharing very well. And we need to acknowledge and represent that because that's going to impact how this individual bond, one, characterizes the entire molecule it's part of, and then two, characterizes the behavior with other molecules, okay, in a larger sample. So it's when there is a difference in electronegativity. Okay. or I think I actually wanted to put partial charges. Okay, which is really talking about the difference in electronegativity between the two atoms. Okay, so go ahead and try giving it a little practice. I want you to, one, draw, okay, determine, I should actually say calculate the electronegativity difference, okay? And then two, draw, okay, a dipole moment between the two. So go ahead and use Pauling scale and go ahead and solve these right now. All right, so you should have gotten the following. For the first one, a bond between carbon and chlorine, the absolute value of the electronegativity difference according to the Pauling scale is 0.5, which would qualify it as polar. So that means we can draw a dipole arrow or a dipole moment showing there's a separation of the charge partially. There's a separation of partial charge. It's not a true charge because a true charge includes a full transfer of electrons. So the separation of partial charges, we have a partially positive region and a partially negative region, and that would be shown by this, or you could write it with delta positive, delta negative to show the partial regions, or for those of you that just need a little extra color in your life, all right, I'll color code the zones. Okay. The next one would have been an electronegativity difference of 0. So it's nonpolar. So we just can't draw a dipole arrow because there is no difference. There is no partial charge regions. And then the final one is between hydrogen and fluorine. And we actually know this as an example of ionic. It's so polar. It's so bad at sharing. All right, that there's actually a complete charge transfer. Now, this also explains why, despite hydrogen and fluorine both being nonmetals, which would usually qualify it as covalent. Okay, so despite hydrogen and fluorine both being nonmetals, which would usually qualify it as covalent, this is why we treat it as ionic, because the electronegativity differences are so great. So there are a couple types of solids that we can look at when looking at covalent structure solids. The first is called a network covalent structure, and you can kind of think of it as like one giant molecule. It's like where we see individual molecules suddenly just molecularly bond to one another. Okay. It's all bonded together. And they have very high melting points and boiling points, okay, compared to those ionic salts, which also are quite high, okay? But what they have in common is that the structure is connected through bonding, through actual bonds, okay? And that will become important as we continue on in our lesson to distinguish molecules interacting through bonding versus molecules just interacting through attractions in general, okay? And then the final one is molecular solids, which is where we're going to talk about that really important difference between the idea of molecules interacting through bonding and molecules just simply interacting. All right. And molecular solids are connected through IMFs. IMFs are what we call the forces between molecules that aren't an actual bond. Okay. So these solids, okay, are connected, or what they do is individual molecular units. So individual molecular units are connected through, okay, intermolecular forces. But they are not actually bonded together. So just a little overview on the ionic versus covalent, because that's where the AP focuses on. We don't really mess too much with metallic, though I will introduce a little bit about it. There's like maybe a couple questions on the MCQ about metallic, but the big idea in terms of the main bond types that we're looking about, which is ionic and covalent, is that ionic, okay, generally speaking, okay, is as a solid stronger. Generally speaking, very generally. Okay. That's because the actual structure itself is, again, one giant bond, right? The lattice structure of cation to anion. Covalent, however, can be stronger. Okay, not just as a solid, but in general, can be stronger than ionic when, okay, when they are polymers, which is basically chains. Polymers, which is like a chain of repeating bonds. Okay, or the mass, okay, of the mass is larger. The mass of the molecule, I'll put molecule, I think that'll be better for you. Molecule is larger, which means that there's more electrons being shared. So for example, the bond between CH4 chain requires a lot of energy. So if I had a chain where I had just a bunch of repeating CH4s connected, okay, and actually it really becomes CH4s and then a 3 and then end with the CH4. I'll explain why that matters in a little bit, okay? But essentially, repeating similar structure over and over again, okay? This would actually have an incredibly, all right, pretty high melting point and boiling point, indicating pretty strong bonds happening right now, because of the fact that there's just so many electrons being shared across the molecule, making it unfavorable or very difficult to break apart. All right. So that will come with a little bit more understanding. If you didn't really get that, don't worry. It'll become clearer as we progress. So quickly for metallic bonds, let's just do this third and final one that's kind of like a side piece, but you do have to know a little bit about metallic bonds. So first and foremost, metallic bonds are formed between, you got it, metals. You cannot have a metallic bond with a non-metal. It is just not okay. All right. So they're formed between metals. And what we say is, generally speaking, because there is, okay, no solid structure to these types of bonds. Oops, what am I doing? There's no solid structure, okay, to these bonds. Okay. What we see is that a metallic solid is easily compressible and therefore tends to be very dense. Now, what do I mean by there is no real solid structure? Well, for metals, metallic bonds are formed between metals, okay, by sharing, or I should really say pooling, by pooling electrons together. So remember, metals kind of want to lose their electrons and gain and have someone else take it. So what if, as a metal, what if you can't find your anion partner, okay? Well, what you can do is you can get a bunch of your other metal friends together and you just go and you pool every electron that you have and you kind of create what we call this sea of electron bond, sea of electrons kind of pool or bonding zone where then you guys kind of like meet each other's needs. You're technically getting rid of your electrons. And what you have then is this kind of fluid, non-superstructured, no one's really claiming an electron here, non-structured form, okay? Non-structured bond attachment between these atoms or non-structured electron arrangement or atomic arrangement to lower overall energy. All right. It's kind of like when you go to a dance and you go with your platonic group of friends, couldn't really find somebody. No, not because of you. Just didn't happen to have someone go with you at an individual kind of level. So what do? You all kind of pool together and you just kind of go as a group and you meet each other's needs and you kind of just do that, right? You kind of meet each other's needs for companionship. So A similar idea with metallic bonds. And it's actually this loose kind of fluid, non-structured bonding reality that allows them to be actually incredibly dense. Because if we just have the sea of electrons, an almost fluid-like behavior, all right, we can just squish them together. We can get them really tightly packed. There's no necessarily particular position they have to be in or region. They just kind of all go together. So this is also explains why they're highly conductible. This is also explains why they can pass heat and electricity so well, and they're bendable. Is because of the sea of electrons, right? Because there is no real structure, because of the fluid, okay, sharing of electrons. There is easy transfer of heat / electricity and manipulation of shape. All right. So generally speaking, when we do look at a solid metal that is bonded through the metallic bonding method, we can kind of categorize some patterns that we see. One is when we have particularly, remember an alloy is a mixture, a solid mixture of metals. Okay. What we see is that if we have a solid metal, okay, theoretically a solid metal would have all the same size atoms and the pool of electrons would be in between, just like sharing. And we see that we call it just a simple pure metal sea of electron structure. Now, what if with your alloy mixture, you have a slightly smaller metal being mixed with another metal? Okay. We generally call that how they kind of end up compressing together to make it all fit. We call it substitutional alloy because one metal, though, is a slightly smaller than another metal, but it's similar enough shape that it ends up kind of creating still a relatively cohesive packing. Okay. But what if you have a mixture where there is a drastic size difference, not just a little smaller, but incredibly smaller? We call that interstitial alloys. And so that when they're compressed, we see that the really small metal atom in the mixture, one of the components actually fits in between the other metal atoms, allowing it to again become very dense and compressed. So that's just kind of a couple of terminology things. You might see that in an FRQ, and it just is kind of good background. But generally speaking, metals don't have that much structure, right? So that's the end of that lesson. You now should go on to your AP problem walkthrough video, and best of luck, you guys.